Welcome to Unit 5, Lesson 1, Growing and Shrinking Practice Problems. Okay, let's look at the first problem here. Select all sequences that could be geometric. So, when we see the word all, that lets us know that there's more than one answer to the problem. So, let's go through each sequence and see which ones are geometric. Now, we know geometric sequences multiply or divide to get to the next term. So now that we know that, let's us go through each number. Okay, so for the first one, 2 to 4 is plus 2, 4 to 7 is plus 3, 7 to 11 is plus 4. We're not adding or multiplying the same number, so that A is neither geometric nor is it arithmetic. For B, 1/3 to 1. How do we get there? I'm not worried about it. 1 to 3. You could plus 2, but that doesn't get you from 3 to 9. What if we do 1 times 3 and then 3 times 3? So times 3, that makes this one geometric. So B is an answer for the next one. 1 plus 2 plus 2 plus 2. This is plus 2. That's an arithmetic sequence. Okay, how do we get from 1/2 to 2? Not worried about it. 2 times 4 is 8. 8 times 4 is 32. So this is times 4. So D is definitely one that works. What about E? How do we get from 1,000? If I knock off the zeros, 10 divided by 2 is 5. So that's dividing by 5. Let's look at problem 2. A blogger had 400 subscribers to her blog in January. The number of subscribers grew by a factor of 1.5 every month. Since then. Write a sequence. So our instructions are to write a sequence to represent the number of months, 3 months. Okay, so we had to start with our numbers. In exponential equation, we have y equals a times b to the x. A is your start or your initial amount. That's your start. This is your growth factor. And x is your variable. Now, you must understand what your variable stands for. So we got to dig deeper into the equation like you did in Algebra 1 with functions. So we had 400. So 400 is our start. Our growth factor is 1.5. And x in this situation means month. Okay? All right, so now, when we put this into the calculator, we're going to push the y equals button in the top left. We're going to put this into the calculator. To make an exponent, make sure you hit the caret, which is over the division symbol, and then hit second graph to read the table of values. So if we had to write a sequence, at 0, we're at 400. At 1, we were at 600. When x is 2, y is 900. When x is 3, y is 1350. So 0 months, that's what she started with. 1 month of reading measurements, the second month of reading measurements, and the third month of reading measurements. You know, you were quick to say that I had 4 numbers and I could stop at 2, but we need to stop at the third month. And this is why we put things into the calculators and look at the numbers. Tyler says that the sequence 1, 1, 1 of repeating ones is not exponential because it does not change. Now, we could write this in an exponential form. Or just 1x, 1 to the x power. This is an exponential equation, but the output, 1 times 1, comma 1, comma 1, comma 1, does not grow. So you could say yes. This is a weird question. You could say yes because you could write this as an exponential, but in reality, no, because when you look at the graph of an exponential function, it should look like this. If we were to graph this function or this sequence, it would look like this. It does not grow. This is not exponential. I do not, in reality, I would say that this is not exponential. You can make an argument for both cases, but in reality, the graph does not grow. Okay, writing exponential functions. In 2000, invasive plant species covered 0.2% of an island for 5 years. That's a time. That means about half by 2005. So we started in 2000. We forgot tripled every year. Every year. Every, each, and per are rate words. So in linear functions, they go next to the x. In exponential functions, they are go next to the b. So since time is our variable, that must be the x. So what did we start with? 0.2%. Now, for this one, we're going to put the percentage right in because we're looking for a percentage as an output. One half equals 0.5 as a decimal. When you multiply this by 100, you get 50, which is a percentage. So a decimal, a fraction, and a percentage are all the same thing. And if you don't believe me, you can always do that in the calculator. The fraction bar always means divide. Whenever you see a fraction bar, it always means divide. The top number divided by the bottom number. So 0.2, it tripled every year. That's our B. And then X stands for years. X equals years. You have to understand what the variable means. If you don't, it will be hard in upcoming lessons when we have to change the variable. So now, from 2000 to 2005 is 5 years. So we put this in the calculator. When X is 5, Y is about 48.6, which is close enough to 50%, which, yes, the student was correct. A square picture with solid length 30 centimeters is scaled. So the lengths are reduced 60%, and then it's scaled 60% again. So we're multiplying 60 each time, so that's our rate. So I'm not going to worry about the questions yet because the first thing you have to do is write your equation. If you don't understand how to write the equation, you're not going to get any of the questions right. So in an exponential, y equals a times b to the x power. We started with 30 centimeters, so that's going to be our input and our output. 0.60 is our factor because we have to multiply by 60 each time. And x is photocopies. All right, or times photocopy. That's better. So we're going to put it in the calculator like this. And then when x equals 2, the solid length y equals 10.8. Now, what is the solid length at 4 times? So when x equals 4, what does y equal? And then we scroll down and we get 3.9. About, I rounded it off. So in the calculator, it should say 3.888, but I'm rounding this off. Oh, I think I forgot to say, to turn a decimal into a percentage, we have to divide by 100. Now, you might be asking, why did we use percentage in the previous problem? The percentage was the input and the output in the previous problem. Here, the percentage is the growth factor. We do not use percentages as growth factors. They must be numbers. So this is the difference between this problem and the last problem. A geometric sequence. As soon as you see the word geometric sequence, write divide and multiply. Starts 5 to 15. So when we have to ask ourselves, how do we get to from 5 to 15? Well, we multiply by 3. So when we wrote geometric sequences, our start was 5, our growth was 3 to the x power. Now, here's the thing with sequences, what people got off on. If x equals 0, then this is good. But if you're starting your x at 1, if you call 5 the first term and not the 0th term, then let me do this in a different color to be clear. And you gotta really think about this and choose what you're doing. If you start x at 1, then you have to subtract 1 to get back to the 0th term. So if we just put the blue part in the calculator, you will see 5 pop up when x is 0. If you put the red part in the calculator, 5 will pop up as the first term. So why don't you put the blue part in y1 and then copy it, do the same thing in y2, but put the -1 part, and you'll see the difference. So it's just a place where you start. And if you're going to have x minus 1, then you need to say that x is greater than or equal to 2, because you got to be bigger. So if you want to if you call 5 the first number, then you need all the rest of it. If you call 5 the 0th term, then the blue is sufficient. Now, to answer the question, you take, going back to the blue one, you take g of 50 to get the 50th term. Or if you're using a red one, where you want 5 to be the first term, g of 50 would be g of 5 to the 3 to the 50 minus 1. So basically the difference between these two is, where do you start? Are you starting at 0 or are you starting at 1? And if you're starting at 1, then you need your second term starts the series. It's kind of goofy, but if you calculate it, it'll make sense. Okay, select all expressions that are equal. So we got more than one possible answer here. So let's see. 3 to the 6. What if I did 3 squared, and when I raise a power to a power, I get 3. This equals 9 cubed. That's not 9 to the 4th. But if I come down and do the next one, 3 squared to the 4th, that is 9 to the 4th. So B works. C works. When you multiply the same base, add the exponents. For D, if I take the exponents 4, oops, I always forget to get off marker. If I do 4 minus a -2, I get 6. So that's 9 to the 6, which doesn't work. 3 to the 4th times 3 to the 4th could be 9 to the 4th, because you got 3 squared to the 4th power, because they had the same exponent. Even though they're the same base, I could do this. So E works. Yep. Sorry, I meant to put on the highlighter here. This one erase. All right, y'all know what I'm trying to do. So B, C, and E.